Good morning, everyone. This is the audio lecture for visually impaired student on the topic Raman spectra. Journal introduction. It is a special type of spectroscopy which deals not with the absorption of electromagnetic radiation but deals with the scattering of light by the molecules. It is observed that when a substance which may be gaseous, liquid, or even solid is irradiated with monochromatic light of a definite frequency mu, a small fraction of the light is scattered. Rayleigh found that if the scattered light is observed at right angles to the direction of the incident light, the scattered light is found to have the same frequency as that of the incident light. This type of scattering is called ray-light scattering. From C.V. Raman of Calcutta University, however, observed in 1928 that when a substance, gaseous, liquid, or solid, is irradiated with monochromatic light of a definite frequency, the light scattered at right angles to the incident light contained lines not only the incident frequency but also of lower frequency and sometimes of higher frequency as well. The lines with lower frequency are called stroke lines, whereas lines with higher frequency are called anti-stroke lines. Raman further observed that the difference between the frequency of the incident light and that of a particular scattered line was constant depending only upon the nature of the substance being irradiated and was completely independent of the frequency of the incident light. If mu I is the frequency of incident light and mu s that of particular scattered line, the difference del mu is mu I minus mu s is called Raman frequency or Raman shift. Thus, the Raman frequency observed for a particular substance are characteristic of that substance. The various observations thus made by Raman constitute what is called Raman effect, and the spectrum observed is called Raman spectrum. Thus, in a simple way, Raman spectrum may be represented as shown in figure 3.29. Explanation for observing Rayleigh line and Raman lines. When the incident photon hits the molecule, this collision may be elastic or inelastic. Elastic collision means that the colliding particles will return with the same energy. Thus, the scattered photon has the same frequency as that of the incident photon. This explains Rayleigh scattering or Rayleigh line. However, if the collision is inelastic, still the law of conservation of energy will hold good. Total energy before collision and after collision must remain the same. Thus, some energy may be transferred from the incident photon to the molecule so that the scattered photon has lower energy and hence lower frequency than that of the incident photon. This explains the occurrence of Stokes lines. Alternatively, some energy may be transferred from the incident photon to the molecule so that the scattered photon has higher energy and hence higher frequency than that of incident light. This explains the occurrence of anti-Stokes lines. This explain may be further elaborated as follows. When the photon strikes the molecule, the energy is absorbed by the molecule and it gets excited to some higher level. Now, if it returns to the original level, it will emit the same energy as absorbed, and thus we have Rayleigh scattering. However, in most of the cases, the excited molecule does not return to the original level. It may return to a level higher than the original level, thereby emitting less energy than absorbed. These explain the occurrence of Stokes lines. Thus, as part of the energy of the incident photon remain absorbed by the molecule so that molecule has higher energy than before. Alternatively, the excited molecule may return to a level lower than the original level, thus, more energy is emitted than absorbed. This explains the occurrence of anti-Stokes line. In this case, the molecule has less energy than before. The different cases may be represented diagrammatically as shown in figure 3.30. Levels have been shown equally spaced just for sake of convenience. Polarizability of the molecule and Raman spectra. The Raman effect arises on account of polarization, distortion of the electron cloud of the scattering molecule that is caused by the electric vector of electromagnetic radiation. The induced dipole moment mu depends upon the strength of the electric field E and the nature of the molecule, where the quantity of alpha depends upon the nature of the molecule and is called polarizability of the molecule. Thus, polarizability is the ratio of induced dipole moment to the strength of the electric field. In case of atoms or spherically symmetrical molecules such as CH4, SF6, etc., same polarizability is induced whatever to be the direction of the applied electric field. They are said to be isotropically polarizable. Such molecules are said to be isotropic molecules. In case of all diatomic molecules, homonuclear or heteronuclear or non-spherical molecule, non-spherical rotors, the polarizability depends upon the direction of the electric field. For example, in case of a hydrogen molecule, the distortion produced is more when the electric field applied is parallel to the bond that when it is applied perpendicular to it, and we write alpha parallel greater than alpha perpendicular. Such molecules are therefore said to be anisotropically polarizable. Types of molecules showing rotational Raman spectra. A molecule scatters light because it is polarizable. Hence, the gross selection rule for a molecule to give a rotational Raman spectrum is that the polarizability of the molecule must be anisotropic, i.e., the polarizability of the molecule must depend upon the orientation of the molecule with respect to the direction of the electric field. Hence, all the diatomic molecules, linear molecules, and non spherical molecules give Raman spectra, i.e., they have rotationally Raman active. On the other hand, spherically symmetric molecules such as CH4, SF6, etc. do not give rotational Raman spectrum, i.e., they have rotational Raman inactive. These molecules are also rotationally microwave inactive. In fact, this is one of the reasons for importance of rotational Raman spectrum spectroscopy over infrared spectroscopy because the latter requires that the molecule must have a permanent dipole moment, whereas the former only requires that polarizability of the molecule must change during vibration. Explanation of Raman effect in terms of polarizability. The polarizability alpha of the molecule that is rotating or vibrating is not constant but varies with the frequency of vibration or rotation. It is the sum of two parts with first equilibrium polarizability, i.e., the polarizability when the atoms of the molecular are in their equilibrium position. Second, sum of polarizabilities of the molecule due to various rotational and vibrational motions, each term depending upon the frequency of rotation or vibration. Thus, where alpha n is the polarizability associated with the nth rotational or vibrational mode and Rn is the maximum displacement of the atoms involved. Further, the electric vector of the electromagnetic radiation varies with the time in a sinusoidal manner as E is equal to E naught cos 2 pi mu naught t. Substituting the values of alpha and E from equations 2 and 3 in equation 1, we get These expressions consist of three terms. The first term has the frequency of the incident radiation and represent ray light scattering. The second term contains mu naught minus mu n and represent Stokes lines, whereas the third term contains mu naught plus mu n and represent anti-Stokes line.